We've been learning how to draw Lewis structures for molecular compounds to use as our blueprint for many things that we're going to be talking about over the next few days. We can use Lewis structures to help us figure out if a molecule is polar or nonpolar. We can use Lewis structures to figure out what intermolecular forces attract one molecule to another. And we can also use Lewis structures for what we're going to talk about in this lesson, which is figuring out the molecular geometry or the actual shape of a molecule if it were in 3D space. So basically our Lewis structures act as a blueprint for us. And then we can use a reference sheet, which you should have with you today. Your reference sheet is titled Electron and Molecular Geometry, Shapes of Molecules, and it has several different shapes based on the combination of how many bonds and lone pairs there are in the particular molecule. So what I'm going to show you how to do is how to, first of all, draw the Lewis structure and then use that Lewis structure to figure out what shape that particular molecule would take if it were in 3D space, what it would actually look like. Okay, reasons for figuring out the shape. It can tell scientists or you if that particular molecule is able to react in a certain way. And there's different theories that explain how these particular shapes come about. The one that we use is called VSEPR theory. When we say VSEPR, that's short for valence shell electron pair repulsion theory. And what this theory basically says is that because electrons have a negative charge and that bonds and lone pairs are made of electrons, that the atoms will arrange themselves in a molecule so that the bonds and the lone pairs are as far away from each other as possible. So we know that electrons have the same charge and they don't want to be that close to each other because when they have that same charge, they push away. We see that electron repulsion. So what you end up with, depending on how many atoms are in the molecule, is a shape. And that shape comes from the pushing away of these bonds and these lone pairs from each other. There are bond angles formed. We don't ask you to actually know these bond angles this year, but there are bond angles formed, different bond angles formed based on these electron repulsions. Okay, so the first thing that we have to be able to do to decide what shape a molecule will be is correctly draw the Lewis structure. Probably the most important thing that you are going to do in this unit is draw Lewis structures correctly, because that correctly drawn Lewis structure tells you so many things about that particular molecule. One of them being this, the molecular shape. So the very first thing you're going to do is draw your Lewis structure. You're going to look at the central atom and count how many bonds and lone pairs are around that central atom. Those areas around the central atom that have, it's either bonds or lone pairs, they both count, are referred to as areas of electron density because there's a lot of electrons in a bond, or there's two, but there's a heavy electron presence in a bond and in a lone pair. Then you're going to look at that reference sheet called Electron and Molecular Geometry, Shapes of Molecules, and you're going to put together the combination of bonds and lone pairs to figure out what shape the different molecules will be. And we'll work through some of that so that you understand that part. You are going to have to know parts of this reference sheet for your test, not all of it, and we'll talk about which ones you'll need to know, but you will have to know parts of it. Okay, so let's go through and practice this a little bit. On your notes, you're going to be drawing the correct Lewis structure for each of these three different molecules, and I'll show you how we use that Lewis structure to count and figure out bonds, lone pairs, and ultimately the shape of our molecules. So we're starting with CH4. So in the box for CH4 that says Lewis structure, I want you to draw the correct Lewis structure. And remember, when we draw Lewis structures, the very first thing we do is count the valence electrons. So carbon has 4 valence electrons, each hydrogen has 1, and there's 4 of them. So there's going to be 8 electrons in my final picture, my final Lewis structure. Okay, carbon is going to be in the middle because hydrogen can't. Hydrogen can only form 1 bond. And besides, whenever carbon is in a compound, put it in the middle. It's most likely your least electronegative nonmetal. So put it in the middle, bond all of your hydrogens, and go back and count your total electrons in the picture to make sure that it's drawn correctly. So we have 2, 4, 6, 8 total electrons. All the hydrogens have 2 electrons, and the carbon has 8, an octet, so that picture is done. To figure out the shape of this molecule, CH4, I'm going to look at my reference sheet, and I'm going to also look at my Lewis structure, and I want to look at the central atom, which is carbon, and I want to count any bonds and lone pairs that are on that central atom. So I have 1, 2, 3, 4 bonds around my central atom and 0 lone pairs. There aren't any lone pairs on carbon. So my combination of bonds to lone pairs is 4 to 0. 4 shared sites, those are bonds, and 0 lone pairs. That combination on my reference sheet, when I look and I find the combination 4 bonding regions and 0 non-bonding regions, is the shape called tetrahedral, and it shows you a molecular picture of that shape. We're not asking you to tell us bond angles, so you don't have to do that part. It actually is filled in on this table for you. What it's showing you is that the angle between each one of these bonds is 109.5 degrees. All right, so for the next one, NH3, I'm going to do the same thing. I'm going to count my valence electrons. Nitrogen has 5, and I have 3 hydrogens, so 8 total valence electrons. I'm going to put nitrogen in the middle of my drawing and attach all the hydrogens to it. And nitrogen has 2, 4, 6. It needs that extra lone pair so that it has an octet. And I have 2, 4, 6, 8 total electrons. So this picture is correct. Now I'm going to count the bonds and lone pairs around my central atom. I have 1, 2, 3 bonds and 1 lone pair on that central atom. So my combination is 3 bonds and 1 lone pair. When I look on my reference sheet, the combination for 3 bonds and 1 lone pair is a shape called trigonal pyramidal. Okay, and I've recorded that here. The bond angle that it gives me for that particular shape isn't really on your reference sheet because you don't have to know that. But if you'll notice, it changes a little bit on this table because that lone pair is putting more stress. It's pushing away those bonds more than the bond in CH4 did. All right, and then finally we have water. We've drawn water quite a bit. Hydrogen, there's 2 of those, so that would be 2. Oxygen is 6, so I have 8 total valence electrons that need to be in my structure. I'm going to put oxygen in the middle and attach my hydrogens. And remember, we said if you ever have a combination of 2 lone pairs and 2 bonds, you gang up those lone pairs on one side of the molecule. It gives them more space. Okay, they have more room to be close to each other. They get more space by being on one side of the molecule paired up. And when I go count my bonds and lone pairs, I have 2 bonds and 2 lone pairs. So that combination of 2 bonds and 2 lone pairs on my reference sheet gives me the shape bent. Notice the bond angle is getting smaller, and that's because these lone pairs are pushing and putting more pressure on those bonds, pushing them closer together. All right, again, don't have to know the bond angles, but you do need to know the process of determining the shape using your reference sheet. Okay, at the bottom of this page, it just says, notice that the shape of the bond angle depends on whether there are lone pairs. And you saw the bond angle getting smaller and smaller the more lone pairs were added to that central atom. All right, so we're going to practice drawing these Lewis structures and using our chart to figure out the shape. Okay, so boron trichloride. So boron has 3 valence electrons. My chlorine, there's 3 of them, and each chlorine has 7 valence electrons. So that gives me 24 electrons that need to be in my picture. Boron is the least electronegative, so I'm going to put it in the middle, and I'm going to bond all of my chlorines to boron. I'm going to make sure that everything has an octet. Okay. At this point, you may realize that all of your electrons have been used up. So I've used 8 times 3, I've used all 24 electrons, but boron doesn't have an octet yet, and it's not part of CNOPS, so it can't double bond, and chlorine can't either. Boron is one of our few exceptions that can actually have less than an octet, and it's okay. It can hold less. It's a very unstable molecule because of that, but it can hold less than an octet and form that compound. All right, now our job here is to figure out the shape. So remember, we're going to look at the central atom, which is boron, and we're going to count the bonds and lone pairs only on the central atom. So there's 1, 2, 3 bonds, 0 lone pairs. So I'm going to look at that combination on my sheet of 3 bonds, 0 lone pairs, and I see the shape trigonal planar. So I'm going to write down trigonal planar. Okay, so I'm going to do the same for ammonium ion. We've actually drawn this one before. Remember, when it's an ion, we have to make sure we pay attention to adding or taking away electrons based on the charge. So nitrogen is 5. Each hydrogen is 1. This means I lost an electron, so I have to take one away from my total count. So that gives me 8. Nitrogen goes in the middle. Okay, and I've used 2, 4, 6, 8 electrons, and everything has an octet that needs it. But remember, I have to draw my brackets to show that in order for this to form, an electron had to be lost. But I want to know the shape of this interior part. Okay, so I'm going to go count the bonds and lone pairs around nitrogen. There are 4 bonds and 0 lone pairs. So when I look on my reference chart, the combination of 4 and 0 is the shape called tetrahedral. Okay, and then finally is sulfur hexafluoride. We've also drawn this one before. This is that gas that makes people talk like Darth Vader. So let's draw that one again. We've got sulfur that has 6, and we have 6 fluorines that each have 7. So that gives us a grand total of 48 valence electrons. Sulfur needs to be in the middle. And then I'm going to draw my fluorines attached to it. Okay, and I'm going to make sure everything has an octet. Okay, and in my picture, I have 48 electrons drawn, so I've used all my electrons. It may bother you a little bit that sulfur has more than 8 electrons, but remember that there are certain elements that atoms can hold more than 8. It's called an expanded octet. Anything that is on the periodic table, any elements in periods or rows 3 through 7 can hold more than 8 valence electrons due to d subshells coming up and holding those extra electrons. Okay, but let's look on our reference chart and figure out the shape of this really big molecule. So in this particular molecule, I have 6 pairs. The combination of 6 bonds and 0 lone pairs is a shape called octahedral. And it gives you an idea of what that molecular shape would look like by its drawing, the molecular geometry drawing. Okay, so that gives you an idea of how to use your Lewis structure to figure out the actual shape of your molecule. One other thing we want to talk about is something called hybridization. It's really easy to do, but the idea behind it is based on something called valence bond theory. So it tells you to remember that covalent bonds share electrons. Well, they do this by overlapping their valence subshells. And remember, the only subshells that are involved in valence electrons are the S and the P subshells. Okay, so it says in a covalent bond there may be 2 s orbitals overlapping to share, there could be s and a p overlapping, or there could be 2 p orbitals overlapping to share. But those are our valence subshells, and those would be the ones overlapping where this sharing of electrons would go on. Now, there is something called hybridization that makes this possible. It says evidence shows that CH4 exists with 4 identical bonds, and they're each at a particular bond angle. So how is that possible with what carbon has as an atom on its own? So to understand that, let's look at the actual orbital notation of carbon to kind of see what's going on. So for carbon, in its valence shell, there is an S subshell that has 2 electrons, and then it has in its P subshell, remember that P has 3 orbitals, okay, and carbon is only using as an atom, it only needs to use 2 of those subshells. So essentially carbon has 4 valence electrons that it's willing to share. However, the way that they're set up in these individual orbitals as when carbon is an atom makes it hard to understand or to see how that would be possible. So there's something that happens with these actual orbitals called hybridization. One thing you can think about that may help you understand this is when you mix paint together. Okay, if you have pink paint, if you have white paint and red paint, those are 2 different colored paints. Okay, just like we have s orbitals and we have p orbitals. Those are 2 different types of orbitals. Well, when you mix white paint and red paint together, you don't see the red and white anymore. It's actually a new color. It's pink. When these 4 orbitals blend together, okay, they hybridize, they're actually going to make new orbitals, hybrid orbitals, okay, where there's still 4 orbitals, 1, 2, 3, 4, but each one of those orbitals can hold 1 electron ready to be shared with another atom. Okay, those hybrid orbitals are named after the orbitals that were dumped together and blended together to make these new hybrid orbitals. Since it took 1 s and 3 p orbitals to create our hybrid orbitals, we call them sp3. Okay, so that's where the name of those hybridized orbitals comes from. All right. And this just explains it a little bit more. It says the 1s orbital and 3 p orbitals are blended and creates 4 spaces for each valence electron for the central carbon to occupy. And we name them after the orbitals that make them up. So sp3 is the name of the orbitals for that particular, for carbon. Now, to figure out hybridization, again, you have to be able to draw the Lewis structure. Like I told you, Lewis structures are really important, and it is really easy to figure out the hybridization once you know how to do it. So you're first going to draw your Lewis structure. You're going to count the number of bonding sites and lone pairs around the central atom, just like we did when we were figuring out the shape of our molecules. And then we're going to use this sequence, S1, P3, D5, F7, to write the name of our hybridized orbitals. Our hybridized orbitals are going to be named based on how many of these orbitals we had to actually use that blended together to hold our shared electrons. If you'll notice, the number that goes with it, 1, 3, 5, and 7, that is how many orbitals are in each one of those subshells. So that should look a little bit familiar. All right, so we're going to use that sequence, and we're going to write the letters and add the superscripts until they reach the total number of sites. That'll make a lot more sense when I show you how to do this. Okay, so we're going to start with CH4, and we're going to figure out its hybridization. So first I need to draw the Lewis structure. I've already drawn this one today. Carbon is 4, and we've got our 4 hydrogens, so that's 8. Carbon goes in the middle, and it's attached to my hydrogens. Carbon has its full valence shell, and all the hydrogens have their 2, or their duet. Now, it tells me to count the number of bonding sites and lone pairs around the central atom. So I've got 1, 2, 3, 4 bonding sites and 0 lone pairs. That's a total of 4. 4 plus 0 is 4. Okay? Now, I'm going to use my sequence S1, P3, D5, F7 to write the hybridized orbitals. Well, I'm going to need 1 s orbital and 3 p orbitals. That adds up to 4. 1 and 3 is 4 to actually hybridize together to hold all the electrons that are going to be necessary to share for this particular molecule. So my hybridization is sp3. Okay? Let's try carbon dioxide, CO2. So carbon dioxide, carbon has 4 valence electrons, and then we have 2 oxygens that each have 6. So that's 12. And we need to, 14, 16, and add. Okay. So we need to figure out what is going to go in the middle of our picture. We've actually drawn carbon dioxide before as well. Carbon's going to go in the middle. It's the least electronegative. And I'm going to attach my oxygens. And if you remember, carbon dioxide is that one that double bonds to the oxygen. Okay? So I've got 2, 4, 6, 8, 10, 12, 14, 16 electrons, and everything has an octet, so my picture's done. The hybridization for this, I want to count the number of bonding sites and lone pairs on the central atom. I have 2 bonding sites. Double and triple bonds count as a bonding site. Okay, so don't count those twice. So don't count each double bond 2 times. It is 1 bonding site for hybridization. So I have 2 bonding sites, and I don't have any lone pairs, so 2 is the number I get to help me figure out my hybridized orbitals. So I am going to need 1 s and 1 p orbital to hybridize together to hold these electrons, the shared electrons. 1 and 1 adds up to 2. So my hybridization is just sp for carbon dioxide. All right, let's do PCl5, which is phosphorus pentachloride. So for phosphorus, my valence electrons are 5, and then I have chlorine, which is, there's 5 of them, and I have 7 valence electrons each. So that is going to be 40. And I need to figure out what's going to go in the middle of my picture. Phosphorus is the least electronegative. It's to the left of chlorine. I'm going to put it in the middle. Okay, and I'm going to attach my chlorine. Okay, 1, 2, 3, 4, 5. I'm going to make sure that everything has an octet. Right, a little squishy. Sure. All right, let's make sure we have everything we need. There's 5 chlorines, and each has 8. 8 times 5 is 40. So I've used up all my electrons. phosphorus is holding more than an octet. And it's okay for it to do that because it is in period 3. It can have an expanded octet. So let's do the hybridization for this. I'm going to count my bonds and lone pairs on the phosphorus. There's 1, 2, 3, 4, 5 bonds and 0 lone pairs. So 5 total is my count. I need 5 orbitals. So I'm going to need 1 s orbital, all 3 p orbitals, and there's 4, and I'm actually going to need a d orbital to help out. And that's what we said with periods 3 through 7, d orbitals come up and help out. So those actual d orbitals are going to have to come hybridize to create enough spaces to hold all these electrons around phosphorus. All right, let's do our very last one, sulfur hexafluoride, and we're familiar with that too because we've drawn it. I am going to erase a little bit so I have some space to draw sulfur hexafluoride. Okay. All right, so sulfur has 6 valence electrons and each fluorine has 7. So I've got a grand total of 48 electrons. Remember, this is a really big molecule. Okay. Make sure all my fluorines have their octet. Okay. And I've used up all 48 electrons. So I'm going to figure out the hybridization. So I'm going to count 1, 2, 3, 4, 5, 6 bonding sites. There are no lone pairs, so my grand total is 6. For my orbitals, I need 6 orbitals to hybridize together. So it's going to take 1s, all 3 p orbitals, and 2 d orbitals. 1, 2, 3, 4, 5, 6. So 6 new orbitals are going to form, and we're going to call those sp3d2 orbitals. So the d had to come up to help hold all those electrons again. Sulfur is in period 3, so it's okay for it to have that expanded octet. It can hold more than 8. All right, so you're going to get a lot more practice with this, but know that this is here for you to refer back to if you forget any of the steps in figuring out the molecular shape or how to figure out hybridization.